Let's move to the next method of heat transfer, radiation. A very interesting topic and also important for your JEE Advanced. Not in mains. In mains, you'll they ask simple questions, but in advance you will find good questions on radiation. What is radiation? As I have already told you, that radiation is the heat transfer by electromagnetic wave, right? So let us start the radiation by Prevost's theory of heat transfer. Prevost says that if there is any body, any particular body, right? Suppose this is a body which is at temperature T1, there is another body which is at temperature T2. Then Prevost says that irrespective of the temperature T2, it is greater than T1, less than T1, equal to T1, whatever it may be, this body will radiate heat in the form of electromagnetic wave due to its temperature. Right? This radiation is due to its temperature, independent of the surrounding material or surrounding temperature. Even if it is a temperature less than the surrounding temperature, it does not matter that it will not radiate. It will radiate heat energy. Only thing is that its temperature, if it's absolute zero, then it will not radiate. Otherwise, if its temperature is more than 0 Kelvin, always it will radiate heat. Similarly, this body doesn't matter what is in front of it, it will also radiate heat in the form of electromagnetic wave I am talking about. Right? Then how the temperature of the body changes to attain thermal equilibrium? It is not that it will radiate, it will also absorb some amount of energy that is incident on it. So if the rate of absorption is more the rate of emission, then its temperature will rise gradually, and if the rate of absorption is less, temperature will fall gradually, and if they are same, it is in steady state. Right? So according to Prevost's theory, every possible temperature, not at absolute zero, there is a continuous heat energy exchange between body and surrounding, and this exchange carry for infinite time. Right? For infinite time means even if they attain thermal equilibrium, both the temperatures are same, this radiation will continue, but their rates will be same. Right? Yes.
Sir, how will a body radiate energy if the surroundings is at lower temperature to it?
It doesn't matter that what is the temperature of the surrounding. Radiation is only because of the motion of the charged particle that is surface at the surface of the bodies, right? So if its temperature is more than 0 Kelvin, then there is always a small amount of vibration, whatever it may be. If its temperature is very small, so the vibration is also very small. If temperature is more, vibration is also more. So the bodies, the particles, they start vibrating, and due to this vibration, actually these electromagnetic waves are generated. Right? At absolute zero, there is no vibration, no EM wave. So the vibration does not depend on the surrounding temperature, right? So if it vibrates, it will radiate heat. But yes, if you are saying that if it is if it's equal to surrounding temperature, then whatever heat it radiates is the same. It absorbs,
Okay, sir.
right? But both of them will simultaneously happen. It will absorb as well as it will radiate. You cannot stop them because it is because of the vibration. Now, there are few bullet points that you need to remember about this radiation. The first thing is, while radiating heat in the form of electromagnetic wave, wavelengths can be in a wide range. So, if the body temperature is T1, does that mean it will radiate heat for a particular wavelength? No. It will radiate heat for a wide range of wavelengths. So, if I plot the intensity of the radiation versus the wavelength graph, you will see that intensity. What do I mean by intensity? Intensity is equal to power per unit area, right? Remember that intensity is equal to power per unit area. So if I say that out of this total intensity emitted by the body, means per unit area, whatever is the power it is emitted, that power consists of several wavelengths. Now if I plot the wavelengths, you will find the function to be something like this, right? So that means if you are looking for intensity of wavelength lambda 1, you will find that is the intensity corresponding to lambda 1, that is the intensity corresponding to lambda 2, like this, right? Lambda 1, lambda 2, like this. So this is E lambda 1, this is E lambda 2. What is E lambda? E lambda are known as spectral emissive intensity, right? What is spectral emissive intensity? Can you define what is spectral emissive intensity? It is the intensity emitted by the body for a particular wavelength, yes or no? Can you understand this definition of spectral emissive intensity? Spectral means for a particular wavelength or frequency. Spectral means this one, for a particular wavelength or frequency, right? This is called spectral emissive intensity. Few definitions you need to understand here. Spectral emissive intensity, here I have written intensity of radiation for a particular wavelength is known as spectral emissive intensity. And if I have to find total emissive intensity for all the wavelengths, then what I will do, I will integrate E lambda d lambda, yes or no?
Yes.
And this area under the graph is equal to total emissive intensity, right, which is integral of E lambda d lambda. So area under the graph gives you the total intensity in the form of electromagnetic wave or radiation by the body for the particular temperature. Have you understood this one? What is spectral emissive intensity and what is total emissive intensity? Right, okay. And few part of this emission also comes under the visible light ray. Sometimes you find that if you heat some object, you will see that its color is changing, right? You will see it is red hot, or you will see that it is white, right? The reason being that now the wavelength falls inside the visible light region, right? Not always. For few particular energy only it will come under this wavelength, right? Okay. So these two points we have understood. Now the third point is any body can absorb heat partly or fully that is incident on it. Fraction of the total intensity observed that is incident on it is called absorptivity. So what is absorptivity? If there is a body, suppose this is a body, right? So few amount of energy is incident on it. Incident intensity, suppose I am talking about intensity, means for a small cross section area, per unit cross section area I am talking about intensity. So out of that intensity, few part will be absorbed in the body, right? So few part will be absorbed. This absorbed part is only responsible to change the temperature of the body, right? So if few part is absorbed, a fraction is absorbed, then what are the other parts? Other parts may be reflected. Reflection intensity is there, right? So if the body is very shiny, it can reflect the waves, and another can be transmitted, right? So there are three different ways where this incident radiation is used. One is absorbed, another is reflected, another is transmitted. Mostly we talk about opaque body where transmitted is zero. For opaque bodies, transmitted is zero. So only reflected and absorbed part is there. And the ratio of I absorbed divided by I incident is the absorptivity or small a of the body, right? It is the property of the surface of the body. If you polish that surface, more amount energy will be reflected, less will be absorbed, like this, right? It depends on the surface of the body, right? Now we are going to look up for a particular body which is known as black body. What is black body? Which can absorb all the intensity that is incident on it. So what is absorptivity of a black body?
1.
1. Right? Absorptivity of a black body is equal to 1. Right? It will absorb all the radiation that is incident on it. Ideal black body is means ideally it is not possible that it will absorb everything, right? But theoretically we can assume few bodies to be black body, right? One such black body very close to black body was made by this configuration. You can understand the configuration, that I have made a small hole inside a sphere, and energy, suppose wave is entering this small hole, and I have made a shape something like this inside. So what will happen? This wave will reflect like this and reflect like this, again reflect like this. So it will get reflected and it will get trapped completely inside it, right? Although you can say there is a chance that it will come out from this hole, but the chance is very small, right? So before it comes out, it gets absorbed inside the body, right? So this is also an example of black body.
Sir,
Yes.
sir, that whole thing is a black body.
Yes, that body is a black body. If I do, it's look, black body depends on the surface. So the actual statement should be the inner surface of the body acts as a black body. Right? I do not know about the outer surface, but the inner surface definitely acts as a black body.
Okay, sir.
Okay. Now there is last one definition, which is the ratio of total emissive intensity emitted by a body at a temperature to the total emissive intensity emitted by the black body at the same temperature. So what is emissivity? Suppose at a particular temperature I have found the area under this graph for a body, and I have got a black body, and I have found the same area of the graph for a black body at the same temperature. So it is E of the black body at temperature T divided by E of the body at temperature T. Right? Okay. So this ratio is the emissivity. দরজাটা লাগিয়ে দাও তো।
Sir,
দরজাটা হ্যাঁ বলো।
is it E of the black body by E of the body or E of the body by
Acha,
the E
yes,
of the
yes, I have written a inverse ratio. E of the black body is always more than E of the body. Right? So the value of E is not greater than 1. It is always less than or equal to 1.
Sir,
Yes.
sir, in the example of the black body that you have given, it is the rays being reflected. So is it being absorbed?
Yes, yes. Whenever each ray is incident on the surface, few part is reflected, few part is absorbed. So in this way, ultimately all of the parts are absorbed.
Okay.
Okay. So these are the few definitions that we should look for in this radiation chapter. And the next is Kirchhoff's law. Kirchhoff's law says that the ratio of emissivity to absorptivity is same for all objects. So for a particular object, if I say E by A ratio is same for all, I can say E by A ratio is same for black body also. So what is E by A ratio for a black body?
Less than 1.
It is 1. For black body, E is also 1 and A is also 1.
Yes, sir. 1.
Right. So that means E is equal to A. That proof is not important, but this theory is important, that E by A ratio is same for all. And actually E is equal to A. That also means that good absorber is a good emitter.
Yes, sir.
Right?
Sir,
Yes.
sir, does emitter and transmitter mean the same?
Emitter and?
Transmitter?
No, that are different things. Transmitter is something which transmits energy. Right? Transmits.
So the one that you have shown in the diagram, it is I transmitted. So is that the same as emitted?
No, look, transmission means the same energy which is flowing through it. The same incident, few part is flowing through it. It is not this body does not affect this one. It is transmitted. Emitted, here I have not shown emitted radiation. What is emission?
The body itself.
Emission is for the temperature of the body. Even if incident, all this part, these three are due to the incidence part, right? And if I say that there is a temperature of the body, then body will emit some radiation due to its own temperature. It is called I emission. Have you got it? If I ask you what is the total radiation out of the body, then you can sum up this one, and this one. These three are the radiation that is coming out of the body. And this is the radiation that is going into the body. But emission is strictly for the body for its own temperature. Have you got it?
Yes, sir.
If I talk about radiation, that is summation of all of them. Radiation out of the body, right? What, because you do not know that which radiation is for reflection part, which is for emission part, which is for transmitted part. You do not know. So the net radiation is the sum of these three, right? And net incident is this one. Anything else you want to know from this slide?
Sir?
Yes.
Sir, by seeing that it is a good observer and a good emitter, can we tell how the object will look like?
Yes. Observe.
How the object will look like, or we can't say that because that means wavelengths will be in a wide range, so it may not be visible.
Yes, the radiation that may or may not be visible. That you cannot say that always it will be visible. It does not also depend on the material. It also depends on the temperature. Right? And good absorber equal to good emitter, that is for all the bodies. It is not only for black body. For all the bodies it is true.
Okay, sir.
Alright, I think it is clear to all of us what is the radiation. Different terminologies. Spectral emissive intensity, total emissive intensity, absorptivity, black body, and the emissivity. Okay, we are going to use them in next discussions. Very important is now Stefan's law. Stefan's law says that the amount of radiation emitted per second per unit area. What is that? It is nothing but intensity of radiation emitted, or emission intensity, yes or no?
Yes, sir.
This is nothing but the emission intensity, right? The amount of emission intensity by a body, by a black body, look, it is talking about black body, is directly proportional to the fourth power of its absolute temperature, right? So what is the emission intensity? It is directly proportional to T power 4. Right? Emission intensity, do you remember what was emission intensity? Can anyone tell me what is emission intensity?
The definition.
Yes, what is emission intensity?
The power per unit area.
Power per unit area, not power per unit area. Emission intensity is the power per unit area emitted due to its own temperature. Right? And it was more on, this is the area under this graph. Can you tell me? Yes or no? It is talking about the area under this graph or not?
Yes, sir.
Yes. So it is the total emissive intensity talking about. So total emissive intensity is directly proportional to T power 4, and the constant of proportional known as Stefan's constant value is 5.67 into 10 power minus 8. Very easy to remember, 5678. 5.67 10 power minus 8. Right? So E is equal to sigma into T power 4. If I say there is a body which is having a temperature T, surface area of the body is A. Can you tell me how much is the emissive power, not intensity? What is emissive power of this body? What is emissive power of this body?
Sigma A T to the power 4.
Emissive power of this body is sigma into A T power 4, yes or no? Because sigma into T power 4 is the intensity. If I multiply it with area, I can say it is the emissive power of the body, which is sigma A T power 4. Is this for all the bodies?
No, sir.
It is only for which body?
Black body.
Black body. But if this body is not a black body, then can I find what is emissive power?
By multiplying with E.
E, yes. Because we know that E is the ratio of the intensity by black body, intensity of the body divided by intensity of black body. So if I know intensity of black body, then E times of that will be intensity of a body. And if I multiply it with area, then I can find what is emissive power of the body, E sigma T power 4. Yes or no? Now, there is another term that you need to understand. I want you to understand this thoroughly, because this part is not given in any of your textbooks. So you need to understand this. This says that if the surrounding temperature is Ts, this is the surrounding temperature which is constant, right? Surrounding temperature is Ts, body temperature is T, surrounding temperature is Ts. Then they say in your textbooks you will find that it is written just after Stefan's law. Everywhere it is written that then the amount, the intensity or the power of heat absorbed, right? It is written that heat absorbed is equal to E sigma ATS power 4. This is the heat absorbed and this is the heat release. So now if they are the same, then the temperature will not change. If they are the different, then temperature will change. That is the simple thing of radiation. But you need to understand one thing, that this heat absorbed is not coming inside Stefan's law. Stefan's law only talks about the emissive power, that also for a black body, right? But this heat absorbed, it is not in Stefan's law. We can actually prove it, that heat absorbed is equal to E sigma A into Ts power 4. Right? A is the area of the body, not area of the surrounding. Right? Now I'm trying to prove this. Right? And you see that what are the assumptions that I have to take for this thing to write. Suppose this is the body. Suppose this is the body and the surrounding is the black body. That is my assumption. That surrounding is a black body. Surrounding is a black body and the area of that surrounding is AS. Area of the body is A. Temperature of the surrounding is Ts. Temperature of the body is T. Can you tell me what amount of energy is emitted by the surrounding body? What amount of energy is emitted by the surrounding body? Can you tell me? From Stefan's law directly you can say that.
Sigma A Ts to the power 4 into time.
Sigma which A? AS or A?
As.
As into Ts power 4. This much is the surrounding body emitted radiation by the surrounding body. Now one question, will all the radiation that is emitted by the surrounding body fall only on the body? Yes or no? My question is, will all the power or energy per second that is radiated by the surrounding body will only fall on the body?
No, sir.
Definitely not. Right? If you see that any particular cross section area, if you take, this particular area is radiating not in one direction, but it is radiating in every direction, right? So basically it is known as hemispherical radiation because this radiation is inside a hemisphere. Can you understand what I have drawn here? A small body can emit radiation in a hemispherical manner. So few radiation is again going to hit back the surface itself. Yes or no? And few radiation is going to hit the body. Right? So let us assume that if fraction of the energy emitted by the surrounding hits the body, right? So F is fraction of the power emitted by surrounding that hits the body. So what is incident energy or what is incident power to the body? What is power that is incident to the body? Is that the same thing that I have written? Sigma AS TS power 4, or is it the F fraction of sigma AS TS power 4? What is the power that is incident on the body?
F sigma.
F fraction of this power that is emitted by the surrounding. Right? Can I say that intensity of incident intensity is F times sigma AS TS power 4. Right? Now there is something that I will write. I cannot prove it because the proof is not in your syllabus. Right? But we will use this particular concept to prove this one. It says that fraction into area is a constant. What does that mean? Actually, it is proved uh, with the concept of solid angle, and also the proof involves a robust calculation, right? So we will not go into that proof, but it says that if this is AS and if fraction of this AS hits the surface A, then F into AS is equal to area of the body into the fraction of the energy emitted by the body that hits the surrounding. Can you tell me what is that fraction? What fraction I am talking about? Now I am talking about the fraction of energy emitted by the body that hits the surrounding. What is that fraction?
1.
Is that 1? Yes. Because surrounding is surrounded by the body, so whatever energy the body will send will definitely hit the surrounding. right? So F into AS equal to A into 1. Fraction of the power emitted by a surface that is incident on another surface multiplied by that surface area is equal to constant. For any other body, if you multiply this area and that fraction, you will equate those, right? So I can say that incident intensity is equal to F into AS. Can I replace it by A? So is it sigma into A Ts power 4? Yes or no? Can you see that?
Yes, sir.
Then what is the intensity that is absorbed? Do you remember a ratio of incident and absorbed intensity? Or absorbed by incident? What was the ratio of absorbed by I incident?
A.
Absorptivity. A, yes. Right. So what is I absorbed? Can I say it is A times sigma A Ts power 4? And what is A? From Kirchhoff's law, what I can say?
E.
So is that absorbed intensity is E sigma into A Ts power 4? That is the proof. Actually, it is not given in your books because of this particular concept, which is out of our syllabus, we out of our scope to prove also, right? So that is why I have used here only the formula, but you can remember it if you want, and that I observed I can calculate in this way: E sigma A into Ts power 4. That is heat absorbed and that is heat emission. And now I can say that whichever is more, temperature will rise or fall accordingly. But before going into that, there is another thing that I want you to understand, that if it is the incident intensity and this is the absorbed intensity, then where does the rest of the intensity goes? If this is intensity incident and this is intensity absorbed, then where does the other intensity, other part of the intensity go?
So the surrounding itself absorbs it.
Yes. So can I say that the rest of the part is reflected intensity? Yes or no? I incident minus I absorbed is equal to what? I reflected.
So why are you telling it it's reflected?
Because if this is incident, if something is incident on it, out of this few part is absorbed, so where does the other part will go? Definitely it is reflected back. I am taking a complete opaque body, right? If nothing is mentioned, you take opaque body. Opaque body means no transmission is possible,
Okay, sir.
right? So incident part is there, reflected part is there, and the subtraction of incident and reflected is what? Absorbed.
Sir,
Yes.
so now a part of the I absorbed will go as I emitted.
That whatever is going, it is inside the body, that I do not know, right? Definitely if the absorption part is going to increase the temperature, then emission is also increasing, right? So I do not know what this absorption, what the body is doing with that absorbed intensity. it is increasing its temperature, or the temperature is remaining constant, or something else is happening. I do not know, and I don't bother about that, right? So I will only say that this is the absorbed intensity and this is the emission intensity, I emission. So these are two different things that I will consider, right? And the difference of them definitely will increase or decrease the temperature of the body. And if they are same, then the temperature will remain constant, right? Is this part clear to all of you? Although if you only remember absorb and emissive power, absorption power and emissive power. Absorption power is E sigma at Ts power 4 and emissive power is E sigma at T power 4. If you only remember those, you can solve numerical questions. But for more conceptual questions, you need to understand what is happening when some part is incident on the body. How we come to this heat absorbed equation, right? That is important to understand.
Sir,
Yes.
sir, here the body and the surrounding both are black bodies.
No. Have I taken body to be black body? Body I have not
Sir,
taken black body. Only surrounding I have taken black body.
sir, then the E should vary in both the cases of the heat absorbed and emissive power.
No. This E I have taken for the body itself. When I am finding the ratio of I absorbed divided by I incident, what I have taken? The absorptivity of the body or absorptivity of the surrounding I have taken?
Of the body.
Body itself. So it doesn't matter what is the E will only take the same thing, the same E of the body.
Okay, sir.
Anything else you want to ask about this situation? A complicated situation indeed, I know that, but if you understand it, so clearly understand it, right? It's not that we will only understand the formula part. Okay. So now we'll come to law of cooling. Before that, let us try to find what is the rate of the temperature change of the body if both are not same. So again, I am drawing the situation. It is something like this. If this is a body of temperature T, surface area A, and emissivity E, it is kept well inside the surrounding body, right? So the surrounding is having a temperature Ts, area whatever it may be, it is not needed at all. Then I can say that surrounding is emitting from its inner surface. Surrounding is emitted sigma As into Ts power 4 power, right? Out of that, the incident radiation on the body is F into this one, so which is nothing but sigma A into Ts power 4, right? And rest of the part is also coming back to the surface itself, that you can find just by subtracting. This is the incident part radiation on the body, sigma into A Ts power 4, Out of that, what is the reflection part? Can you tell me what is the reflection part? What is the reflection power? Reflected power? If this is incident, what is reflected? Can you tell me how much is reflected if this is the incident? Tell me if this is the incident, how much is absorbed?
E into sigma ATS to the power 4.
Then how much is reflected?
1 minus E
1
into
minus E.
sigma ATS.
1 minus E into sigma ATS power 4, right? Very simple if you just follow few definitions. And what is the emission? What is the emissive power? What is the emissive power?
Sigma ATS to the power 4.
E sigma A Ts power. Not Ts power. E sigma A into T power.
T.
Right? So for this particular body, in steady state, can I say whatever heat is absorbed is equal to heat emission? Yes or no? In steady state, whatever heat is absorbed is equal to the heat emission. Right? In steady state, or if I am not considering a steady state, if I am not considering steady state, I am considering any state where the temperature is not a constant, then what should I write the equation? Should I write that equation like this? dq by dt incident on this body minus dq by dt that is reflected from the body plus dq by dt that is emission of the body, that is equal to mass of the body into specific heat into d theta by dt. Can I write this equation? Just check.
Yes, sir.
Yes. Out of that, what is the subtraction of dq by dt incident minus reflected? What is this term?
dq dt emission.
It's not emission. dq by dt incident minus reflection is what?
Absorption.
Absorption. Yes, absorption. And what is absorption? If you just subtract it, you will find sigma ATS power 4 and sigma ATS power 4 gets cancelled out. So this will be E sigma into ATS power 4. Yes or no?
Yes, sir.
Minus what is emission? E sigma AT power 4. Can I say that is equal to ms into dt by dt? Instead of theta, you can write T because we are considering the temperature to be T not theta. Yes or no? You can find then from this expression what is the time taken to change the temperature from a certain value to another value, right? So you can say dt is equal to ms divided by E sigma into A into dt divided by Ts power 4 minus T power 4. 0 to T and the temperature is T1 to T2. Have you got it? Yes or no?
Yes, sir.
Yes, sir.
Okay. But as you can understand, the integration is very tough because dt by ts power 4 minus t power 4, this integration is not an easy integration. Can you do it? This integration, is there any formula of this integration? I don't know. You can do it, but I've never tried because we have some another approximate formula in order to find the time, right? That we will discuss now. Before that, as I have drawn this diagram, if I ask you one question, what is dq by dt of radiation? What should be your answer? Radiation out. What is dq by dt of radiation out of the body? Should I only take emission part?
Reflected plus emission.
Reflected plus emission. Right? Yes, just 1 or 2 years back, I think JEE Advanced had this question. What was the radiation intensity, radiation power, I think. And most of the students, they have written only E sigma A T power 4. If you do not know what that there is some reflected part, you will definitely mark this one. But that was a wrong option. Right? The net radiation out should be the summation of this emission part and the reflected part. Right? So you should know this thing. It is dq dt of emission, plus dq dt of reflection. Right? Because you cannot understand which one is for which part. Right? The radiation or reflection or emission, both will be out of the body. Right? And incident is only once. So I think this part is clear.
Both have same wavelength.
Doesn't mean it doesn't mean that emission is also of the same wavelength. Emission can have also different wavelengths. Reflectant can have also different wavelengths. Incident also can have different wavelengths. But what I am doing here, when I am calculating this dq by dt, I am integrating the total wavelength parts, and I have got this one. It is not spectral part; it is the total part. All right. So I think this part is clear to all of you. Next, we will move to a simplified mathematical equation so that we can calculate the time, known as Newton's law of cooling. It depends on some approximation. The approximation or the assumption that we will take here is assumption is surrounding temperature minus body temperature. The difference is small. Surrounding temperature and body temperature, the difference is small. Right? It may be body temperature more than surrounding or surrounding temperature more than body. Right? So the difference is small, that I have assumed. If I assume that difference is small, then suppose Ts minus T is equal to delta T. Right? Then I can write this equation dq by dt, or it's not dq by dt, actually it is written wrong. Dq by dt, yes, you can say dq by dt. We have calculated E sigma A into Ts power 4 minus T power 4 is equal to M into S into dt by dt. That equation we have just calculated in our last slide. Yes or no? Assuming here the temperature of the body is less than the surrounding, so it is gaining heat, so its temperature is increasing. Right? It may also cool down, as the law is a law of cooling, or it may be a heating also. So if it cools down, then I will just reverse that temperature. Right? Okay. So E sigma A Ts power 4 minus T power 4 equal to Ms into dt by dt. Here I will see one thing. What is dt by dt? That is equal to E sigma A by Ms into Ts power 4 minus T power 4. I will now break it. Ts square plus T square Ts plus T and Ts minus T. Now I will apply the approximation part. Ts square plus T square, as they are very close, I will assume both of them to be Ts. So this is 2Ts square. This is also 2Ts. And this is delta T. Right? That approximation I can do because delta T is very much less than Ts plus T. If you say what is Ts plus T, Ts plus T is 2Ts minus delta T. Now delta T is small compared to the surrounding temperature, so that I can approximate to be 2Ts only. Right? So the equation actually talks about dt by dt, which is equal to some constant multiplied by Ts minus T. Right? What is that constant part? That constant part is 4 Ts cube E sigma A by Ms. Right? Or which is written here d theta by dt is actually proportional to the change in the temperature of the surrounding and the body. This is known as the Newton's law of cooling. Right? Now there are two ways to solve this equation again. One, you will get actual answer by integration. By integration, you can find the time dt is equal to dt divided by k into Ts minus T. You can integrate this to find the time. Or there is another method called average method. In this average method, what we do, we take the body temperature, the surrounding temperature Ts. Suppose the body temperature is rising from T1 to T2 in a time T1 second. And if I ask you that the same body, what will be the time if the body temperature rises from T2 to T3? Then what we will write? We will write the same equation, but not we will do integration. Instead, we will write this equation. Dt by dt is the temperature difference divided by time. So it is T2 minus T1 divided by time T1. That is equal to some constant into surrounding temperature minus body temperature. Now what body temperature I will take? Because the temperature of the body is changing inside within this time interval. So average method says that you take the average of the temperatures, T1 plus T2 by 2. Right? This is the number one equation. And for this particular scenario, you will take T3 minus T2 divided by T2 is equal to K into Ts minus average temperature of T2 and T3. Right? And you take the ratio of them, you will find what is T2. The second method is often used, right? It is more often used, the second method, than the integration method. Because in integration method, you will do integration and you will find the answer. Now, which one you should take? It depends on the choices of your question. Now, if you find that in your options, it is given the time is some e power of something like that, then you should definitely understand that we cannot find e power something by average method, right? You should integrate that. And otherwise, you should find the time by average method. Average method is very useful to calculate the approximate time, right?
Sir?
Yes.
So what is the limit till which we can consider Ts minus T equals to small? Is a small quantity?
Yes, actually, even if I am saying that it is small, but even if it is not small, you can take that. Not small means what? Look, here T and both the temperature surrounding and body, we take it as in absolute temperatures, right? Absolute scale. So suppose I say that the surrounding temperature is, let us assume that the surrounding temperature is 40 degrees Celsius, right? So 40 degrees Celsius means how much Kelvin? Plus 273 if you do, then
330.
313.
Yes, sir.
Yes. And suppose body temperature is say uh, 30 degrees Celsius or 20 degrees Celsius also. 20 degrees Celsius. Right. So that is equal to, body temperature is 20 means it is 293 Kelvin, right? You can still say that what is delta T, is it negligible compared to 2Ts? Delta T is 20 and 2Ts is somehow 60, 600 like this, right? So then also you can approximate this value. Ideally we take delta T less than 35 degrees Celsius, right? Or 35 Kelvin, whatever it may be, or 35 Kelvin. For this condition to be true, you will never find that delta T is more than 35, right? Then probably this is a ideal case, right? Means after calculation all of these things, you can find that if it is more than 35, then this approximation formula and the actual integration formula, the deviation is more, right? By calculating you can find, so near about 30-35 degree is okay, you can use it. Anything else we want to know from this calculation discussion, Newton's law of cooling? Okay, I think we are done with the theory part of this radiation. Now we will solve few numerical questions. Most of the questions, yes, this one is also I have taken from one JEE advanced question. So let us try to solve this one first. The question says that this body has a temperature 2T, this body has a temperature 3T, and what is the temperature of this middle part of this plates? Suppose the temperature is theta. They are ideal black body. So if this is 2T temperature, then what is the emission by the black body in this direction? Is it sigma into area into 2T power 4? Yes or no? And this emission is completely going to fall on this plate. Similarly, what is emission by this part of the plate? Sigma into A into 3T power 4. Is that emission also going to hit this plate B? Yes or no?
Sir, it will be C, not D.
Yes, it is
C.
C, yes. So if these two are incident radiation on it and it is also a black body, so what is the absorbed radiation of the by the body?
Emission.
The same thing as that of incident,
Yes.
but it has also temperature theta, so it will emit. And what will be the emission intensity by this one? Sigma A theta power 4, and it will emit from both the surfaces.
Yes.
So can I say 2 sigma A into theta power 4 is equal to sigma A into T power 4, 2 power 4 plus 3 power 4? which is 97. So theta is equal to 97 divided by 2 to the power 1 by 4 into t. That should be the answer of this question.
Sir, why are the plates considered to be large?
Because otherwise I cannot say that all the energy or power that is emitted from this surface going to fall on this one, right? If it is smaller and this is not large, then the energy may not come to this surface, right? It can go out, directly fall on this, or it can go in the space.
Sir,
Yes.
so that means if it is not large, there will be another term, that F, for each of the three plates.
There will be another term of F, means yes, the fraction, yes, that fraction part will come, right? Can you tell me another question, that this all the temperatures are constant, right? So what is the power that I have to supply to this plate externally to make the temperature constant? What is the external power needed to make the temperature of the third plate constant at 3T?
Sir, is it sigma A into 81 t to the power 4 minus sigma A theta to the power 4?
Sigma A?
Yes, sir. Sigma into 81 t to the power 4 minus sigma a theta to the power 4.
81. Achha. Let us check. Look, this body will also radiate in this direction with sigma A into 3T power 4.
Sir, then it will be 162.
Yes.
It will be 152.
And this energy, this power that is radiated by this middle part will also fall on this part,
Yes.
right? These are going to fall completely on this section, and it is going to absorb this power completely. It is also absorbing this power completely. So what is the total power it is absorbed? P plus sigma A theta power 4. And what is power that it emitted? Sigma A 3T power 4 into 2 times of that, right? So P is equal to sigma A into T power 4 multiplied by 81 into 2, 162 minus 97 by 2. Yes or no? That should be your answer.
Yes.
Right? So you should understand what is incoming and what is outgoing from the surface. If you can only write down that outgoing and incoming power, then you can solve any question. Parallel rays of intensity 912 watt per meter square are incident on a spherical black body kept in a surrounding temperature of 300 Kelvin. Stefan Boltzmann constant is given. Assume the energy exchange with the surrounding is only through radiation. What is the final steady state temperature of the black body? So this is a spherical black body, And an intensity, parallel intensity is incident on it. Parallel rays of intensity I is incident on it. It is kept in a surrounding of temperature 300 Kelvin. And its temperature suppose is T in steady state. Then what are the incident radiation on it? Can you tell me what is the incident radiation on it? Or the power incident? Due to this surrounding, what is the power that will be incident on it?
The 5.7 10 to the power minus 8 into 300 to the power 4.
5.7 into 10 power minus 8 into, it is sigma into area,
So
power I am
into
talking
into-
about. Area is 4 pi r square into 300 to the power 4, right?
Sir, but area is not needed.
Area not needed.
It will cancel out.
All right.
It will.
Let us check. And what is the power that due to this intensity part, this intensity?
Sir,
912 watt per meter square is given. I have to only multiply it with the area. Right? So which area I will multiply here?
Projected area, pi r square.
Pi r square.
Yes, I will multiply the projected area because intensity is defined for perpendicular area only. Right? Intensity is not defined for any area. It is defined for perpendicular area. So if you think about this area, this is not perpendicular to the intensity. Right? So I will take this area, which is projection of this part, and multiplying with this intensity, I will find what is the power. Intensity is power divided by area, but that area should be perpendicular to the incident ray. Right? So that is equal to pi r square only, not 4 pi r square. Got it? And what is the power that is emitted or emission? Emissive power? Emissive power is equal to sigma into A into T power 4. Right? Now this incident is equal to absorption. Can I say that?
Yes, sir.
Because of the black body. It is a black body, so incident and absorbed are the same. Then you can just equate these two and find the answer. Right? So in that case, I can say 5.7 into 10 power minus 8 into 4 pi r square into t power 4 minus 300 power 4 is equal to 912 into pi r square. Right? So pi r square gets cancelled out. And I can say t power 4 minus 300 power 4 is equal to 912 divided by 4 into 5.7 into 10 power minus 8. Right? So I think there is a bit calculation. What is this value? 912 divided by 4. If you do it, 912 divided by 4 and 5.7. Right, I think it is 40. It's coming 40, right? 912 divided by 4 and divided by 5.7. So it is 40 into 10 power 8. Right, so T power 4 is equal to, it is also 10 power 8. 3 into 10, 3 to the power 4 is 81 plus 40 into 10 power 8, right? So it is 121 into 10 power 8. So T is equal to 100 into 121 means under root of 11, I think, right? What is under root of 11? It's near about 300 only, but it's slightly more than that. It's 9 root over of 9 more than 9. So it's near about, you can say 330 Kelvin.